Right, welcome everyone. Thank you for coming to this wonderful venue. Thanks to Dolby for having us this evening. A couple of ground rules. There are no drinks allowed in here, so please finish up any drinks that you have. Tonight's lecturer, you probably all know him, John Vanderkooy. So John is a retired physics professor from the University of Waterloo in Canada. And does a lot of work with Bowers and Wilkins on the consultancy side. But tonight he's going to talk to us about a little side project of his to do with infrasound in vehicles. So without further ado, I'll hand over to John. Thank you.
Thank you, Tom. Is my microphone working? No?
It's just for the benefit of the recording.
It's just for the recording?
It's not wired to the computer.
Okay. Well, thank you. Yes, this is a little side project, and I'm glad to see you all. It's just, it's fun. It was fun stuff for me. It started because of what I was doing with. Let's talk a little bit about wind turbines for a moment. When you're measuring a wind, it started because we were measuring wind turbines with a colleague, Richard Mann and Kevin Crowell, and I was doing that, and we'd heard that infrasound was a problem with wind turbines, and there are a lot. If you get onto the web, you'll find a million websites with all kinds of things on it. But I had made a preliminary measurement in my car some time before, and I realized that the infrasound. And infrasound we define as sound that's below 20 hertz. And although it's roughly 20 hertz down to 1 hertz, I'm going to go right down to DC, okay? There's not much there between 1 hertz and DC. It's only 1 hertz, right? It requires a bit of problem with microphones, but anyway, the point is, it's very difficult when you're measuring a wind turbine to shield those microphones from the wind. And it's very important that you do that. The wind noise is strong whether you're away or near the turbine. And it's not clear whether when you see these people measuring wind turbines, it seems to be that in many ways they're just measuring the wind. Anyway, that was the point. The blade passage signal is very hard to measure, and it really is a bit smaller. And that's I think, what people are worried about, that regular thing, that's happening. So here's a wind turbine. And it's about 600 meters away. The microphones are here in the grass somewhere. And that structure there, years ago, my son had a video game, a Coleco video game. It had a pistol, which you aimed at the television, and as the beam scanned across the television, when the pistol would optically see it, it would give a pulse. So it knew where the gun was aiming. Do you see what I mean? And this gun, well, I put it up there in order to aim it at the side of the blade so that we could get a signal from the blades passing by. And I wrapped it in paper. You can't quite see it because I didn't want the local farmer to think that we were going to put holes into his wind turbine. But anyway, it works very well. It generates these pulses. And the thing is, these particular turbines are a Siemens 2.3 megawatt turbine, which generates DC, which is then converted into AC. And the speed of those turbines changes by 20 or 30% during a half an hour, which is remarkable because most turbines are attached to the grid and they keep a constant frequency and they're bang on the mains frequency, or very close, because the generators have a slight slip, but they're very... So that was the optical tracking that we had. This is a typical signal from the 600 meters from that wind farm in pascals here. 1 pascal is 94 decibels, right? 10 pascals is 114 dB. Anyway, you can see here that it's not a very large signal. So the typical level is of this order. And it can go higher. If the wind is higher, then you'll get all kinds of things happening. This is a spectrum, very long spectrum, many minutes of data taken and finally Fourier transformed, and you can see the lines here. This is the second harmonic, the third harmonic of the blade passage frequency, which is about 0.7 hertz. So it takes roughly So it takes 1.4 seconds for each blade to pass. So the total time for the blade rotation is about 5 seconds, something like that. And the thing is, though, the energy in these lines is very small. And this is a turbine that's running at a fixed speed. If I did it to that Siemens one, you wouldn't even see those lines, because the turbine is changing its speed so much that it just gets lost. Anyway, the point is that we were able to take these things here, and what we do is we use the pulses from the blade passage, and we take the long file of the recording, of the microphone recording, synchronously with the blade passage pulses, and we rewarp the time in order to make the time flow perfectly smoothly. It's in machine analysis. We have a local company nearby that does engine research, Ricardo, and they would do this sort of thing. They would have a tachometer mounted on the shaft of the engine, and as the engine runs up and down, they can keep track of all the Fourier coefficients because it's what's making the pulse. In other words, time is in what is called the revolution domain. Rather than the time domain. It's in the revolution domain. And that's what we did. And when you do that, you can actually see what happens. This is an example of one of the what we do is we warp the time so well that the coherent output from the wind turbine sits precisely on a bin. It has no leakage, no spillover. And so here's what it is. But you see the scale is very small. So this is a very weak signal. And my point is that if this is audible, okay, or if this is bothering people, then a car should drive us nuts. And that's the point. I mean, it really is amazing. So that's how we came to it. Okay, so what about that? Well, there is this guy, Alex Salt, Dr. Alex Salt. He's a well-known researcher. He's done a lot of research on neuroscience of guinea pig ears, I think. And they measure signals, and they find that very low frequency signals can be captured by the ear because there are the outer hair cells, the last row of hair cells, is actually coupled to the basilar membrane in such a way that they're DC coupled. There's actually ligaments that move them. And so these hair cells can produce output at 1 hertz or 2 hertz. You don't hear it because it's not connected to the audible part of your brain. But it's there, and he can measure it. And he says anything that's over about 60 dB, G-weighted, I'll talk about that, you can hear. Okay, fine. I don't believe him, but that's fine. He's got a lot of people that do believe him. And the second point is that the wind noise is not related to the wind turbine. The wind noise is really large cells of air moving around, and because they're moving, because their pressure is a little lower than the average atmospheric pressure, and that's a chaotic system. Weather is terribly chaotic. So it just makes random noise, and we'll see the spectra of some of that random noise. So, I mean, there are pros and cons for infrasound, right? But I'm a con. I think it has been a con, actually. So we won't go there, maybe. Okay, here is an example of a spectrum from a turbine and a spectrum from a vehicle. Look at the difference in the scales. I mean, yes, this turbine, this is not a very windy day. If it's more windy, it'll be up to 75, even up to 80. But the point is, the car is 20 decibels louder. So that's the beginning. And, I'd intended to say that in about 20 seconds, and now it's been 5 minutes already. So the talk is probably going to last a little longer than half an hour. I'm sorry about that. But anyway, there we have a vehicle spectrum. And you see here that this is 1 hertz, right? That's 1/10 of a hertz. And it's fairly flat there. That's typical. This was my Honda Civic driving to the nearest grocery store, the Sobe store. That's why the text file is called that up there. Anyway, here is what Alex Salt thinks we should do with the very low frequencies. Don't A-weight them, because if you A-weight them, everything's gone. So he says, no, these outer hair cells respond to this low frequency DC. This is what you should do. And so you can see it actually gives an increased weighting between 10 and 30 hertz. This comes from an ISO standard. And he says that 50 dBg is detectable. So whether it's dangerous or whether it's even Whether it's noticed by people, I don't think. When detectable means that when he sticks a probe in there, he can measure something with sensitive biological measuring equipment. Okay, infrasound in cars. Well, it's generated because the vehicle is moving. Certain aspects of infrasound are really quite noticeable, and it's much higher than in wind turbines, okay? So there is concern over infrasound in wind turbine noise, and for that reason, I think cars should be studied more. We all get in them, we all drive them, and we know they're not killing us sound-wise. There's fatigue, and there's motion sickness and various things, so who knows? Maybe there are some important things there, but I don't know. This paper is not a health study. I'm just going to tell you what sort of infrasound there is in a few cars that I've measured and let it go at that. Now, here is an example of some mic signals on a bumpy road. And there's a microphone on the ceiling. There's one at the rear deck. This is one on the floor, and this one is at the front on the dash. And so notice that they all give the same signal. That's very important. This is filtered. This data has been filtered at about below 20 hertz. It's infrasound. There may be a little bit of stuff there between 20 and 30, but the filter's dying. And so basically all the microphones are reading the same thing. You might think then that it doesn't matter. Maybe I don't need 4 microphones. Maybe one in the car would do, and that's roughly true. Here are the spectra. This is the spectrum that you saw before. Notice that at the very low end, this is 10 hertz and below, all the microphones are reading the same here, right? That's not quite true here, and that's because these are GRAS microphones, G-R-A-S, Gunnar Rasmussen, the Danish company. And believe it or not, those microphones are different at low frequencies, and that's why they read differently. In fact, I was able to measure them down to 0.1 hertz fairly easily by just sticking them in a loudspeaker box, and then, if the box is well sealed, varnish the inside, then you can measure them right down to 0.01 hertz if you like. So I think I have better measurements of those mics than they do, actually. But it's interesting. Look at here. Above 20 hertz, you can see that the microphones are all doing different things, because now they're in different places in the car, and the panels of the car are moving, and now those near-field signals are meaningful, so that it does that. And here is this curve is normalized accurately in Pascal squared per hertz. Okay, so if you integrate this spectrum here, you'll get the SPL. This one is the 1/3 octave one, and that means that at any frequency here, the SPL in that 1/3 octave is given. And notice that it's almost flat, right? Every 1/3 octave has almost the same energy in the infrasound. Remarkable, I find. What's also interesting is in a curve like this, you can see whether people have done their math correctly. If you think of 1/3 octave at 1 hertz, at 4 hertz, a 1/3 octave band is about a hertz wide. Therefore, at 4 hertz, which is here, these two curves should coincide. And if they don't coincide, the people haven't done their math right. Anyway, that's just a small point, but you can sort of see that. Okay, well, let's think about a car. The vehicle's a box. Complex shape. The largest car is about 3 meters. I mean, we can talk about vans and so on too, but we're talking this sort of typical distance. There are windows. The car has vents, and we're going to characterize that. So let's look at the car. This is my Honda Civic. I did some measurements in an old BMW I have as well. I did some measurements in a Pontiac, and I did some measurements in a Honda van. But anyway, I just show the, here is the, oops, keep pressing. Here's the microphone sitting on the front console, and here is a subwoofer in the back seat, such that its acoustic center, which is a little bit in front of that thing, is right in the middle of this seat, okay? So it's right on the center line of the car. And we put, now if the car is a sealed box, if the car is a sealed box, and suppose that the cone moved out a couple of centimeters, then the volume inside the subwoofer would increase by a certain amount, and the volume in the car would decrease by the same amount, right? And because of that, those inverse volume ratios, the volume of the subwoofer and the volume of the car, the pressures will be related to that. So if I was able to put a microphone inside the box and this one in the car, then those two ratios of pressure and the volume of the box will tell me how big the car is. I can measure the volume of the car by doing this experiment. Anyway, here is the result of that experiment. This is with the car closed up. Okay, everything's closed up. And notice that it's basically flat. Now, if the car truly were a sealed box, then the response would have gone right to DC like that, right? Because the subwoofer is sealed, car is sealed, right to DC. It doesn't. It goes down. It's sort of first order-ish, but it's sort of going to second order. Anyway, that's a high-pass filter. And the reason it's there is because the car has vents. The air conditioning, the heater, the vents at the back, which will let the air out. In order to find out where those vents at the back were, I went to the local salvage yard. I said, can I look at some of your horrible cars? And they said, sure. And he said, have you got a camera? I said, yes. He says, give me the camera, because he didn't want me to take any pictures, because these cars have been in accidents, and I guess there's legal ramifications for that. Anyway, this is interesting. So these things change as the trunk is open and the window is open and the frequency rises. But just look at this one down here. That 7 hertz filter has a time constant of 23 milliseconds. So any source that's inside the car is going to die with a time constant of 23 milliseconds. So you don't have long to get that pressure. Here are the 4 mechanisms that I included in my paper, and I do not know how good these are. I mean, I don't really know a lot about cars. I certainly don't know much about, body design and so on. But the first one, turbulence from the air motion outside will get in through the vents. One of the people at Ricardo said, well, maybe it's banging the side of the car. Yes, could be. But I think I'm going to put that under category 2. I'm going to say that when your car hits a bump, suppose that the body twists slightly and changes its volume by 1 part in 10,000. Will you give me that? Sure. It's metal, it bends, it's got some elasticity. 1 part in 10,000 isn't much. But atmospheric pressure is 100,000 pascals. That means that change of 1 part in 10,000 will give 10 pascals. You have to multiply that by 1.4, the adiabatic parameter. So it's 14 pascals, which is 117 dB or so, right? So that's unweighted. So just doing that. And I think this is actually the most important feature of the mechanism. There are inertial effects from vehicle acceleration. We'll talk about that. And pressure changes from elevation. You drive up a hill, go down. I mean, you may not notice it, but that's... Okay, so here's the instrumentation in the car. There's a laptop strapped in, because when I do some sudden braking, I don't want it to fall on the floor. There's an accelerometer here that measures the side acceleration, left-right. There's another one here that measures the up-down and the front-back. So there's 2 cables coming out of that one, those 2, and then they all go to the back. And the car is a mess in the back. I mean, whenever you do experiments in a car, there are cables everywhere. Okay, okay, here's the microphone that's sitting on the, let's see, that's on the dash at the front. There's the odometer, speedometer assembly. This is on the rear deck. This is on the roof. And this is taped to near the floor, a centimeter from the floor. So these are 4 microphones and data acquisition system. This is something I'll talk about a little. It's a differential pressure sensor. It measures pressure. It measures it down to DC. There's no high-pass filter in this thing. And I've got a beer bottle back here. This is a North American beer bottle, but it's on the reference port. So if that bottle is there and it's sealed, then this thing will respond to DC, because this is just the inlet port. Now, the trouble with it is that if this gets warm slightly, then the pressure just increases in there and it saturates the device. So I gave it a little bit of a leak, and the leak I gave it was a small bit of micropore tubing, and the leak was about 100 seconds, which means that it goes down to about 10 to the minus 3 hertz. And it was too much. So, but I'm working on changing that. But anyway, this is very interesting, and it will, in the second round of experiments, I will be doing more. This is a road speed sensor. It's made from a little motor from a compact disc player, and the cable just goes in, just generates DC, and you can measure it with the data acquisition system. Okay, so high-speed motion through the air. Well, you try and find a smooth road surface, and they vary a lot. You get away from other traffic. You put microphones at different places in the car, and you record the wave files with calibrated data. And this is typical of the signal. This is filtered again to 20 hertz, right? And the unweighted sound level here is 103 dB, 98 dBg. So, I mean, if Alex Salt is right, we should be hearing this. We should really be hearing this. Probably neural signals going to the brain like crazy, right? But it doesn't bother you, does it? Not me. Well, after a couple of hours of driving, you get tired. Maybe that's part of it, but maybe that's the normal noise. I don't know. Anyway, this is the spectrum of that noise. And this was the smoothest road I could find locally. And it's interesting. Notice that the spectrum has a 7 hertz low-pass behavior, roughly second order. And I think that's the car. That's the leaks in the car. Because what's happening is the turbulence is coming in through those vents. And those vents act like, and the car volume act like a Helmholtz resonator. And its frequency is basically the frequency of that filter, which is 7 hertz. Now, it was a high-pass filter for signals that are inside the car. But if I have signals outside, turbulence coming in, then it's a low-pass filter, right? Because it's going into a closed cavity. Whereas it was sound inside, it's going out into the atmosphere, the open. So it changes whether you're considering it as a source inside or outside the car. Here again are those 4 microphones. Now you'll notice that these 4 microphones are doing the same thing, right? So what does this tell you? It tells you that the sound is the same everywhere inside the car, more or less. There are slight differences between the mics. I'll show you that in a little while. And so let's talk about some other situations. And I don't have the talk that well organized yet. It's got various things, but we'll talk about bumps and slams and braking and vehicles passing by. Okay, here is a speed bump. This is one of my first experiments, and my daughter-in-law had the laptop on her lap, and I found this street with these sleeping policemen, you know, these bumps, right? So I took the first bump at about 40 kilometers an hour, and she said, "You're not going to slow down, are you?" And I didn't. I mean, you go over, you bottom the car, but I mean, it's an experiment, right? So you do anything for that. And so notice that basically all the microphones have the same signal, but not quite. Because there are effects due to this. This is the vertical acceleration, and it's quite high. Notice that it's almost 3/4 of a g, right? -7 meters per second squared. And it's interesting also because that's vertical acceleration. So if you look at it, the upper microphone should have a different signal than the other microphones. This is the microphone at the front. This vertical acceleration, there is some lateral acceleration associated with it too, because when you hit the bump at the front, the car goes up and back like that. Anyway, you can look at this in detail quite a while, and it's hard to understand it all because what's happening is quite complicated. The air inside the car is sloshing back and forth because it's heavy. Air weighs 1.2 kilograms per cubic meter, and you're throwing it around. And because of that, the microphones will have different signals. But basically, they have the same signal, but not when you're trying to accelerate strongly. And so that's interesting. Okay, here is a recording of the microphone. This is the microphone down here, and that's the acceleration up there, right? Note measured, concurrently. Notice that there are bumps, and the bumps tend to show more things. Well, those are not always bumps. I'll show you what they are in a minute. But the acceleration has them too, but they're not the same. The acceleration tends to show more spikes than the pressure. I don't know why. I'm not quite sure. It's interesting because this is the spectrum of the microphone. This is the spectrum of the accelerometer, and the accelerometer has almost a step edge at about 10 hertz. This is the Pascal squared per hertz. This is 1/3 octave. So they're the same curve, just renormalized. And that's a smooth road. The SPL there is not as high. It's 93 dB. This is a door slam. This is a vigorous door slam. I really exercised my arm there. And that's pretty high pressure there. That's about 140 or 150 dB up there. You can work it out. 1 Pascal is 94 dB, right? So 1,000 Pascal would be 30 dB higher than that. 30 dB higher than that? No, that would be 60 dB higher than that. So that would be 150 odd decibels, which is close to what you're getting here. Now, notice that this is quite narrow, right? How wide is it? It's about 1/23rd of a second. Or, sorry, it's 23 milliseconds, because the car, when you slam the door, you're putting a source into the car. You're pushing the air in. It goes out through the vents, and that time constant is 23 milliseconds, right? So that's why you get it looking like this. I don't know what an airbag would do. Have any of you had an accident with an airbag going off? Thank goodness. But I would like to know what you heard or didn't hear, because I think you might find that you don't hear anything for a while. I don't know. Okay, here's another thing. This is a microphone at the rear. This is a microphone at the front, and you see they read much the same signal, except for this. I don't know what that is. This was the baritone, that differential pressure sensor. Now it's calibrated. This is offset by 20, and this is offset by 80 or something. But notice that the is my microphone still attached properly, or is it? Sorry, Nick. Well,
That's all right.
okay.
Is it comfortable?
Yes, it's comfortable. Just make sure it doesn't fall off.
You shouldn't.
Okay, thank you. Notice that the calibration I put in is about right, because look at this feature here. It's the same size there. The calibration of this thing is right. Why is this differential pressure sensor giving these enormous changes? I can explain some of them, but not all of them. Some of them are because you're driving the car along and you're going up and down elevation. Now, every meter that you go, there's a change in pressure of 12 pascals from hydrostatic air. The air has that pressure change. And so that explains a lot of it. But you see, this is more like, 40 or 50 pascals. So that's quite a change. And I don't think the car was going up and down that far. So it could be that the car has got slow changes in volume or something. I don't know, because it should be high pass filtered. So these are changes coming in, and almost static changes, if you like. So I think this is elevation. Now, I have a Dutch friend who cannot stand elevators. Even one story bothers him. His eustachian tubes are not blocked, so I don't know why, but he has... Somehow, some people are bothered by pressure changes, weather, and so on. And I think what's happening, we probably don't know how, but somehow their body is reacting to the absolute atmospheric pressure. And we don't really know why that is, but there are some people that are sensitive to it, and they have this problem. So we don't really know. Here's a roundabout. This is a North American roundabout, and I'll leave you to fit. This is the side acceleration. I've got left and right marked, and you can see whether I've done the right thing or not. English roundabout would be the other way up, right? Okay, here's an inertial effect. Here I've got sudden braking. So I'm going from, smoothly, this is about 60, 70 kilometers per hour, braking down to zero. And so it's almost just over 6 meters per second squared, so almost 3/4 of a G. And then the car stops here, and then very quickly the acceleration is zero, because the car has stopped. The brakes have crunched the car to a stop. And if that's true, then when you brake hard, the air should go to the front of the car, and the microphone at the front should have a higher signal than the one at the back. And it more or less is true. But the pressure change that we expect is about 20 pascals, and we're not getting that there. Well, maybe there's something happening. Maybe the vents at the front are letting that air out the front. I don't know. But when the thing stops, this acceleration change is more abrupt, and we do get approximately 20 pascal difference between the front and rear mic. So those inertial effects are there. And if you've ever taken a child's helium balloon and had it in the car, when you accelerate forward, the balloon will go to the front window. Have you experienced that? And if you put the brakes on, the balloon will go to the rear window, which is contrary to what you'd expect, but that's because the air is heavy, and it's layering itself like that. It's really quite a neat thing to do. I've done it. And it's quite cute. I I was sitting in the car waiting to turn left. I turned the measuring system on because I don't want to touch the laptop when I'm driving. It's not safe. And I was waiting at the stoplight, and 2 cars came by. Whoosh, whoosh. Here are the pass-by signals from these cars. They were about 2 meters away. Roads in North America are wider, so the cars are 3 meters away. These are quite strong signals too. It's interesting because the microphone is properly phased, so the pressure goes positive first and then goes negative sharply, and then various things. So I can't explain it other than when the car is plowing through the atmosphere, there's a bow wave, like a plane going through like a boat going through the water, and that bow wave has this effect. It's really quite interesting. This is a cube van that came by the other direction, and the system just clipped. That has a huge signal, and I think the car went like this, you know. And these are huge signals, huge infrasound signals that come in. Is England different? Well, your roads are narrower, the cars are usually smaller, the road is never straight. And even without frost, you've got lots of potholes, just like we do, plenty of them. Okay, so here's my Picasso. This is my Picasso, which is a modest vehicle, but it's French, right? And it's a Citroën. And I put the microphone in it, I calibrated it, and this is what we get from it. This is the pressure data for a 14-minute run going from Stenning to a little place called Woodmancote. And occasionally, the signal is down here. I'm waiting at the turn. And here I'm waiting for a long turn, quite a while. So anyway, this is it. The microphone responds down to about 1.3 hertz. And I was recording this at 11 kilohertz because there, the digital filter in my Behringer sound box has a cutoff that's almost 1 hertz, so I don't lose so much infrasound. Whereas if I run it at 44.1, it kills it below 4 hertz. And so I went to this frequency, which is fine for the infrasound. Here are the spectra. This is the spectrum in pascals per hertz, and you can see that you know the sound pressure level is about 105 dB, unweighted in the car. And here it is 1/3 octave. Now, the microphone rolls off below about 1.3 hertz, and I've made an attempt to correct it, which is the red curve. It's probably not right. It's probably a little over here. It should be a little bit, but it's probably right. And so, interestingly, the spectrum is roughly flat, like the other one was that I measured with the better mics. Now, if you look back at the data, occasionally you'll see things like this. You see that? Well, here are some of those, and those are pass-bys again, right? And British roads are narrower, so the pass-by, well, he's just about taking your mirror off, right? As you know, and the pass-bys are much stronger here than they are in North America because of the distance to the car. This is the engine noise on this Picasso. It's a diesel, right? And it makes quite a bit of engine. This is sitting there just moving along smoothly on pavement. And this is engine noise. The frequency of this is about 26 hertz. It's fairly audible. It has some harmonics too. And you can see what it came from. It came from this place here, the blow up of that little area. And because the car was moving very smoothly on smooth pavement. And anyway, here is one of the fellows at B&W bought a BMW electric car, an i3. Lovely car, beautiful car. So we went out in it either yesterday or yesterday. And I took this data. And what I like about it is this. Look, when it stops, there's almost no noise at all, right? Because there's no engine. It just stops totally. And here we are. This is going from Stenning down to Shoreham and back. And it's interesting because the spectrum is even higher than in my Picasso, right? So the Germans know how to make infrasound as well. It's not much different, maybe a dB or so. And that could be, now, it could be because that BMW car does not have a B-pillar on the side. If you open the front door, the back door opens backwards. It is the B-pillar. So the whole thing is open then on the side. And I think that body's a bit more flimsy, is wiggling a bit more, and may make more infrasound. I mean, if the body were perfectly rigid, then you should have, hello, Heather. Oh, I shouldn't do that. Anyway, I think this is really interesting. What I did was there's a portion here. From there to about there is the expanded portion here, and you can see this large one here. There is that pass by, and you can see they're very large. So I make the following assertion. I haven't measured too many cars, but I've measured now 3 or 4, and they all have about the same level of infrasound, given a few dB, given the road condition. They're all, and I think basically most of it comes from the bouncing on the road, changing the volume of the body, flexing, and all cars are about the same shape today. They're all made of fairly thin sheet metal. So I think they're all about the same. And I don't, there's not much difference between them. So here are my conclusions. The infrasound in cars is much larger than wind turbines. So if there is, my take on that is that since cars don't bother us too much, we should forget about infrasound in wind turbines. I just don't think it matters. That's my take on it. Okay, the acoustics in a car here is simplified. The pressure is basically uniform inside, except for the gradients when there's acceleration, and they're small, and they're vents, right? The pass-bys and the door slams are large. Incidentally, we came down a few weeks ago in the train tunnels, and we came down today again, John and I, and my goodness, some of those tunnels, when you go through, you can feel your ears popping quite badly. So there are some huge pulses there. I wouldn't even hazard a guess how much. And so maybe the fatigue in the vehicle is perhaps be some cause for concern. But other than that, I think the infrasound in cars is interesting, and I don't think you can do much about it. Thanks very much.
Thank you very much, John.
And you're going to tell them about the microphone.
Fascinating lecture. Do we have any questions? Let's open the floor to questions.
At the beginning, when you were talking about the guy whose name I've forgotten, who thought...
Alex Salt?
Yeah, the Salt.
Yeah.
When you said, is there any neural connection between this basilar membrane and these hairs? So is this DC effect connected to the brain at all?
Yes, it is.
So there is
There
a
are
neural
signals
connection.
going to the brain, and that's why he's concerned about it. But we know that we can't hear it.
No, sure.
But I mean, there are other things happening too. Your ears contain, the vestibular, your balance, your equilibrium. All those things go to the brain, and we don't think of that as sound. But there's all kinds of signals going there, and we don't know what they are. Now, we do know that the French military did experiments in the past, and by putting enough infrasound onto you at 4 hertz, they can make you vomit in about 3 seconds. So there are definitely connections between your ears and your physique. So we don't know. I mean, I think that's why, although I poo-poo the idea of infrasound in wind turbines, who knows? I mean, Alex Salt is a well-known researcher, and I should not be deprecating his work maybe as much. I think we don't know the answers.
Yeah.
Thanks, John. This is all very interesting, but the fatigue aspect is actually quite important, because if you could reduce the fatigue in driving, obviously it would keep the driver more alert, wouldn't it?
Yes, I'll tell you what I wanted to do. The people in Canada, we have a grant to study this, and it's not my grant; it's for another group, but I'm associated with them. They want to produce the sound of a wind turbine in a sleep lab, and then have instrumented students, cannon fodder, doing the experiments, right? And so we want to see what happens to them when we give them these sounds. So in order to do this, I took one of the small equipment rooms at B&W here, and we put a woofer in the wall, sealed the door, and put my DC microphone in, and I wanted to see whether we could pressurize the room to make the sort of levels that we're talking about. And I found that it was very difficult, because when you're talking about things like 1 hertz and 2 hertz, you need an incredible amount of woofer motion. Really large. And so that was the idea. The idea was that we would somehow be able to evoke the problems in a lab situation. And then what we would do is we would take the car noise, for example, and filter it so that the stuff below 20 was separated from the stuff above 20, and see whether the fatigue relates to the audible portion or the infrasound portion. That would be really interesting, I think.
I was just wondering, because of the fatigue element, if you had noise-cancelling headphones, for example, forget the fact that if you can't hear what's going on outside the car, that might also represent a hazard for the moment.
Her Majesty might not like it. I mean, if you don't let
mean if she was trying to address you from outside the car.
Yeah.
You wouldn't be listening like one of her good subjects. I was just wondering if something like a noise-cancelling headphone would actually work down to these sort of infrasound levels.
I think it would be very difficult because the headphone would have to seal very well on the head. I personally feel that the fatigue is probably related to the audible portions and not the infrasound, but one can't be sure. There are very high infrasound signals here, and so it could be that the fatigue, that there's a component of the fatigue related to infrasound. It wouldn't surprise me if that were true. But at the moment, I would think not. Enough of us are doing experiments. So do people that drive cars, are they less happy than people that don't? I don't know. I think it's like radiation from cell phones. Do you believe it's a problem? Well, there's enough people doing it. So I don't know.
John, you mentioned at the beginning how difficult it was to actually record these signals because of wind noise in the microphone.
Yes.
This seems to indicate that wind is a much more serious problem. How much do we know about the spectrum? For instance, I think a few people here have been to the Bolkeshire meeting of the Nordic Sound people, and one of the things they claim there is how wonderfully silent it is, but it's actually a disappointment because the wind noise is enormous in the trees.
The wind noise is enormous, but it is very low frequency, so it's not really audible except in the tops of the trees and so on. When measurements on wind turbines are done outside, the microphone is usually put on the ground and covered with some fiber fill or something, and that keeps it away from the surface wind. In fact, there's an Australian group that feels that you should actually dig a hole and put the microphone down there, have two different layers of wind screens and the top of the screen. So they're all trying to get away from this wind noise. But the wind noise is still going to come through because the air is still making these violent, chaotic things, and that pressure is just going to acoustically accumulate down there. You can't avoid it. And the point is that we did an experiment with a wind turbine, those Siemens wind turbines. We measured them, and then when we were finished, I took the car very quickly. We drove 2 kilometers upwind, took the microphone out in the field in roughly the same situation, and we measured again, and we found actually slightly less wind noise there than at the wind turbine. Well, actually, slightly. It was about the wind noise was slightly more, but there was no turbine blade noise. But the point is that it doesn't matter where you stick your microphone, near or away from the wind turbine, the wind noise is the dominant factor. It's not the wind turbine.
And of course, it's quite a serious problem in trying to do interviews outdoors. I mean, you can't always dig a hole and put
but there. And if you're riding your bicycle, with a helmet or without a helmet, the wind comes past your ears and you hear this rushing noise. I've got some hearing loss in the left ear, and in North America, that's the driver's window. And I'm sure that when I was younger, I drove quite often with that window down, and the roaring noise from that may, over the course of time, give hearing loss. I don't know, but you know what I mean.
Yes, and it's predominantly, I presume, below 10 hertz.
Probably.
And we probably don't notice it because of that.
And it has a spectrum which goes right down. I think if my microphone did not quit, it would keep going right down to the bottom of those graphs, roughly flat. It's quite amazing, really.
Yes, just a thought about comparing wind turbine situation with car situation, and wondering what the influence of the general background level might be, if you like, because if we're driving a car, in a way, we expect it to be noisy, and it is noisy.
It is.
And if one's out on a quiet night with a clear sky in the middle of nowhere in the countryside, then possibly the ambient wind level may be lower and less intrusive than if we're driving a car. And I wonder if that affects our threshold of annoyance, if you like. And particularly with turbines which rotate at a more constant speed, we might perhaps be able to perceive a regular pattern to that.
Well, there is a regular pattern to some turbines, not all, that you can hear like that. And I think David, you're right. Once you start to become annoyed by that, even though it's 30 dBA, you're a goner. Yeah. You will continue to be annoyed by it, and I think this explains a lot of the people that are having health problems, because once it gets on your nerves, you can't shut it off.
Yes.
And I think that's the main cause.
I know in the region where I live, there was quite a lot in the local papers over several months about a very low frequency noise which upset a lot of people. It was eventually thought to be connected with the gas main or something like that, but it covered quite a big area. And I was certainly aware of this, and in the middle of the night when things were very quiet, and it wasn't identifiable as a sound, but it was more of a sensation.
Well, maybe the infrasound would do that, because if there are brain signals and one doesn't hear them, then what are they doing? Why are they there? I mean, I think there are questions that need answers.
You get this with earthquakes, of course.
With
people can sense earthquakes very often in advance.
Well, and certainly animals and dogs and so on do. So what are they sensing? You're right. I mean,
anyway, very interesting, John. Thank you very much.
Yeah.
Well, you've already answered one of my questions earlier. So I know that in my car, I suspect that the noise above 20 hertz will completely mask anything below 20 hertz. Do you think it might be possible to develop something you could seal over your ear, which is a 20 hertz low pass filter? It's like a plate with a small hole or something like this that would filter out.
You would cancel the audible noise.
You would just hear the infrasound noise and nothing else.
I think that would be rather difficult, John, but maybe. I think the seal would have to be really super. It might require a lot of pressure. It might be rather.
But I think that would be very interesting, so that you could actually experience only the infrasound.
Well, one way to do that might be to use a good noise-cancelling headphone, because that probably gets rid of most of the normal sound. They don't work below about 30, 40 hertz. So they also would allow the infrasound in without... So maybe that's a good experiment. I think that would be a really
good experiment,
Yeah. It's interesting that David's point there. Years ago, David, there was my colleague Stanley and I were approached by a lady who lived in a village in a town about 20 miles away, and she said, "You people are the sound experts." She says, "I hear this sound from she lived well away from this town, Galt, and she said, I hear this sound," she says, "and I keep asking people about it and they don't hear it." So Stanley and I Stan went down actually. He took a PCM F1. Do you remember it? And he, with the research mics, and we measured there, we could find nothing at low frequencies. And it was really something, because we had to tell her that we couldn't find anything. Anyway, she asked or telephoned again. And so what I did was I don't know how I learned about it. A friend maybe. There's an organization, and I think it has English base, which is there for people with super sensitive hearing that have problems like that. So I found its address, and I sent it to this lady. Well, about a month later, I got this profuse letter back thanking us for what I had done, because this lady was going crazy with these sounds, but she found now, she talked to some of the other people, they heard the same thing. She felt right away that she wasn't it wasn't her mind going crazy, and she felt better about it, and she felt she could live with the sound. And I hadn't realized that I'd helped her. And I mean, it was amazing, really.
Did anyone come up with what this sound was then?
There was a large stamping machine hundreds of meters away, and it may have been shaking the ground. There could be some. I mean, I think she wasn't kidding. I think she actually had a real cause. It's just that people didn't twig to it. So it may have been infrasound.
John, it might be very interesting to do measurements underneath the flight path of aircraft taking off, because you get a lot of vortices below
Yes.
the aircraft, and that would be quite interesting actually to see if it affects, because it must affect people.
Instrument Heathrow, and yeah.
Or Gatwick.
Well, I think infrasound is very ubiquitous. I think there are many things that generate it, and I think, some of you were saying, I mean, in an earthquake, you've got kilometers of soil moving by millimeters, right? Well, that's bound to generate one hell of an acoustic signal, right? Because where's that air going to go? It's going to generate a huge signal. So I think that, yes, there are things like that we don't fully appreciate.
I think you should come round to my house one Sunday afternoon or something and just leave it running. Because
Okay.
we regularly get the helicopters in.
Okay.
I'm sure they do produce.
Well, we're going to measure your car anyway, John.
What about popping balloons in kitchens, John?
Yes.
I have to wait for the next party, I'm afraid.
John and I were popping balloons
Yes.
in the kitchen 2 weeks ago.
Well, Richard's
Preparation time, so
Richard's done some measurements in the Royal Festival Hall, blowing balloons up, and I was surprised at how effective they were as a sound source to measure reverberation. I'd been using Melissa in other ways, but it really did work very well, didn't it? And I didn't. I mean, you did it. There's experiments for a few years ago, right?
3 years.
Okay. Yeah.
What was so interesting was the repeat off the first reflection. When you slowed the recording right down, it was really just like gunfire. Bang, bang. It was almost the same level.
That's right.
Yeah.
One of my colleagues, Richard Mann, what he does with wind turbines is interesting. When he makes a recording that's, say, half an hour long or an hour long, he takes that recording and then decimates it down so that it's much smaller as a file, and then plays it at a greatly increased time speed. He speeds it up by, say, 64 times, and then that blade passage becomes a growl. You can hear it. Do you know what I mean? And so this is an interesting thing, and we're going to do a bit more of that, because then you can start to think about the character of the sound. You've moved all the frequencies up by a factor of almost 100 so that you can hear them easily. And it's interesting.
Any further questions?
Just a quick one, John. Have you tried doing your measurements with the window slightly open so you're getting that very...
No. Those signals are very large. There are some papers in the literature. I mean, you get signals that are 130 dB. And I find that when I open the window and it goes boo, 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 it drives me crazy. Does it do that to you too?
I was just wondering what sort of levels it are reaching.
I expect 140, that sort of... I mean, they're really high, I think. I don't know. I can do it, but... that's you shouldn't do it. Probably, it's.
Well, thank you very much, John.
You're welcome.